The broadcast is now starting. All attendees are in listen-only mode.
Hi there, and welcome from Studio 27 in Sacramento, California to today's webinar, Materialistic Engineering, Building Stronger, Better Products Using Interactive Tables and Equations, sponsored by Novel and Desktop Engineering, and hosted by WebAttract, your end-to-end solution provider for webinar demand creation. For those of you that may not be familiar with Novel, they're a web-based application that integrates technical information with analytical and innovative search tools to provide answers that engineers can trust. Their users include thousands of engineers and applied scientists worldwide that represent 70 of the Fortune 500 companies and more than 300 leading universities. Hi again, I'm Mike Agron, the executive webinar producer with WebAttract, and I'll be your moderator and one of your hosts for today's session. We're delighted to have you join us. So you can benefit from hearing today's topic. We thought it would be a lot more interesting and engaging for those of you in the audience. We're able to have a panel of experts interact with each other where they could share their insights, best practices, and lessons learned from their collective experience and how they use interactive tables and equations to build stronger and better products. You'll also have an opportunity to have your questions answered at the end of our panel discussion during what we call our Ask the Experts panel session with the panelists, and we'll also be having someone from Novel join. But for now, let's get started. We have a lot to cover, and we absolutely value your time. Thought it'd be interesting to let you know that we have a true global audience that's registered for today's webinar. We've got over 26 countries and over 550 people. We're absolutely thrilled with that, and all of you are representing a very diverse group of industries such as engineering, design, and construction, aerospace and defense, oil and gas, and equipment manufacturing. So thanks again for joining us. And we absolutely believe that regardless of your industry affiliation or role, that you'll find a lot of value in today's webinar. So let's move right into the program. Bring on today's moderator and panel leader, Kenneth Wong. If you're a reader of Desktop Engineering, you probably recognize his name and know that he's a contributing editor. And he's been a regular contributor to the CAD Industry Press since 2000, first as an editor and later as a columnist and freelance writer for various pubs. During his 10-year association, he's closely followed the migration from 2D to 3D, the growth of the product lifecycle management with the impact of globalization on manufacturing, and he's Desktop Engineering's resident blogger. Delighted to have you on today's webcast, Kenneth, and welcome, and how are you doing?
Thank you very much, Mike. Glad to be here, and I'm doing very well.
Terrific. Well, I'm going to turn this portion over to you, and we'll talk with you in the audience in a bit.
All right, great. Thank you very much. Well, welcome, everybody. Let's talk, first of all, about the 3D models and digital models. Now, if you have been in engineering for quite some time, you probably realize that today 3D models and digital models sculpted in computer-aided design software, generally known as CAD, are no longer just a bunch of pixels and pretty renderings. They have become substitutes, or stunt doubles, if you will, of the new kind of products that we are building, whether it may be the wind turbines or the luxury vehicles that are under construction. We explode them, we stretch them, we break them, we rebuild them inside a computer program using special software so that the real thing that we built can be as good as it can be. In many cases, the CAD models or the computer-aided design models exhibit the same material properties and behaviors that physical counterparts do. After all, that's why we can conduct stress tests on digital model. So now, more than ever, the decision that we make about the thickness of a cell phone cover or the radius of a boiler or the width of wind turbine a wind turbine's blade, for instance, I don't think they have to be approximations anymore or the random numbers that you would put in and then later hope that you can perfect by trial and error. They should have hard science backing them to make sure that the turbine's blade can, say, make the best of the wind speed of the region, or the cell phone cover can endure a couple of drops without cracking. I don't know about you, because I've dropped my cell phone quite often, and so far I'm lucky to say that it hasn't cracked on me yet. At the same time, we're also learning more and more about the world around us, about how much carbon is produced, for instance, when we build something in steel as opposed to PVC or plastic, about how much more durable or less durable a bike handle will be if we switch from one material to another. Now, these data can be just a Google click away, a Google search away, but in some special content, technical content providers portals, like Novels, for instance, you can actually export many of these newfound data points about the world around us or about the new kind of sustainable principles that we can now incorporate into our design work, you can export them as interactive tables, charts, and equations like the example that we see now on the screen here. So I'd like to explore the possibility of incorporating equations and tables into the leading computer-aided design CAD programs. And I'm privileged to be joined by two panelists who have made a career out of developing professional design and engineering software in their life. But we're going to meet the panelists very soon. Before we do that, I just want to do one live poll to get the audience, to get to know the audience a little better for us and for the panelists as well. So Mike, can you help me do one live poll?
You bet. And folks, if you would go back to your control panel and raise your hand to the question, how many people in our audience use computer-aided design software on a regular basis? We'll share the results as soon as we get everybody's vote in. Kenneth, the show of hands comes back at 44% of our audience uses computer-aided design software on a regular basis at work.
Thank you very much, Mike. That's great to know because that's nearly half of the audience. So, but for those people who are not familiar with computer-aided design software, we'll try to talk about that in a much more specific terms and explain that a little bit. Okay, time to meet our panelists. Let's start with Amy Bunzel. Amy, how are you doing?
Very well. Thanks, Kenneth. So
Thanks,
welcome,
Amy.
everyone.
Yeah, and welcome to you too, Amy. And can you tell us a little bit about who you are and what you do?
Of course. So I've been with Autodesk for the past 7 years. I'm responsible for Inventor, our flagship 3D mechanical modeling application. And that's really the heart of our digital prototyping solution. I actually studied electrical engineering at Cornell University and went on to get a master's degree from UMass Amherst. Simulation has played a major role in my career and actually started in the electromechanical space. And as I've transitioned from the electrical space to the mechanical, it's been great to see increased adoption of all kinds of simulation, from functional design to full-on multi-physics.
Thank you very much, Amy. Glad to have you here. Okay, let's meet Sandy Jong, our other panelist. Sandy, can you also say a few words about who you are and what you do?
Sure, Kenneth. Hello, everyone. I'm responsible for product marketing for PTC's desktop solutions. I've worked on launching several new product releases for ProEngineer, Co-Create, CAD-5, and MathCAD. Like Amy, I also have a technical background, and it is in materials science and engineering. I have a bachelor's and master's from MIT. This discipline studies how the structure of materials and manufacturing processes affect the performance and ultimately the design of products. I've done research in aerospace materials, polymers, ceramics, and semiconductors. A few examples include the mechanical stress, strain, and fatigue properties of metal alloys used in aerospace applications, the performance of specialty ceramics used in space shuttle applications, and also mechanical properties of semiconductor materials used in the high-tech and electronics industry. So the topic of today's webcast is therefore very near and dear to my heart.
Well, glad to have you both. Thanks, Amy and Sandy. Let's talk about equations and tables now. I am familiar with computer-aided design software, but I want to ask you, because you have made a career out of developing these kind of software. Start with Sandy. Sandy, is working with equation-driven dimensions, shall we say, is that a common way of working among people who use PTC's computer-aided design packages?
Okay. Yes, Kenneth. Working with equations is very common among PTC customers. A majority of our customers are CAD customers that use ProEngineer, which was the first parametric modeling system introduced to the market roughly 20 years ago. And one of the core principles of parametric modeling is using variables and equations to drive geometries. Many of these capabilities are automated, so you don't see the equations. You simply change input variables. The equations are then recalculated in the software's intelligent algorithms, and then the geometries are automatically updated. This slide shows how equations can even be edited within ProEngineer using the relations editor. So as you can see for this crankshaft design, there's an actual equation in here as well as some annotations that show how these equations control the symmetry and the counterweights that are used in this particular model.
Thanks, Andy. Amy, how about you? What do you see among Autodesk customers? Is that method of using equations to drive dimension, is that a common way of working?
Yes, absolutely. I agree with Sandy. In fact, driving dimensions from equations is a great way to take advantage of parametric modelers like Inventor and ProEngineer. You can think of it as easily as having a box and always wanting the length to be twice the width. Or if you think of a variable pattern where the spacing might change as you get further from the starting point, you can control all of this by controlling relationships. In Inventor, we use a parameter editor as the starting point. And you can access it easily through our task-based Ribbon UI. It enables you to name parameters, enter equations, and even hook up to Excel.
So let's get a little more specific about this if we can. Amy, suppose someone wants to use an equations to drive the curvature of a blade or the thickness of a shell part or the radius, whatever the dimension might be. How do they do that? Now, I've been also hearing a lot about this feature called iLogic in Autodesk Inventor. Is that the right function to try to deploy?
Yes, with Inventor, iLogic is embedded in the product, and it's a great way to take equation-driven design to a new level. It allows you to add logic when creating rules that drive your parameters. This really helps when creating intelligent families or even configurators, as you can see in this example here. In this next image, you can also see a glimpse of the environment that's used to create these rules. I think of this as being as easy as creating Outlook rules with all the power of Lisp, programming language that's used by a lot of our AutoCAD users. A big benefit here is that it captures your design intent. So it's obvious to anyone who uses this component or part later on why you created the design the way you did. So for example, if you wanted to control the thickness of that plastic part based on the material selected or some other variable, you can create the rule right within iLogic, and then that rule and that logic is visible to anyone else who edits your design in the future. Another benefit of driving the parameters intelligently with equations is that you can create standards across your company, and that allows some consistency in your design practices.
Amy, I have a follow-up question, and Mike, stay on that slide for a little bit longer, if we may. Now, what I'm looking at here looks like programming languages, but I've also dabbled with iLogic function a little bit, but this is not a function that requires deep understanding of programming, is it?
That's correct. It's very much a drag and drop. You can see you get a list of all the available parameters. It's all color-coded, so really you're entering very little information, and the system is doing the majority of the work for you. Again, I liken it to kind of when you create a rule in Outlook to kind of organize your mail folders. It's very simple and straightforward, and you don't need to be a programmer.
Yeah, if I can teach my Outlook to able to intelligently distinguish the junk mail and the useful mail, that would be very helpful. I'm still having trouble with that.
I haven't created a mind-reading program yet.
Unfortunately. Sandy, we'll turn to you now. Are there ways in which PTC users can also incorporate the same kind of equations into the workflow? How should the workflow be structured around equations? You have some thoughts about that?
Yes. So actually, as you can see, equations are critical to various different aspects throughout the product development process, all the way from product requirements through conceptual design, detailed design. A lot of these equations are driving either design decisions or the actual CAD geometries, or they're supplementing some CAE or analysis process as engineers and manufacturing engineers are developing products to deliver them to the market. So there are multiple ways in which these equations can be used within ProEngineer as, again, an engineer takes their concept and design and moves it down this process. So very early on in the concept phase or product requirements phase, if their intellectual property and their equations are captured in a program such as MathCAD, our products work together, so MathCAD and ProEngineer naturally integrate, and you can take those parameters from MathCAD and automatically drive the geometries within ProEngineer. Within ProEngineer itself, like Inventor, it's got a very flexible way of accepting data, variables, and input from multiple applications. So not just MathCAD, you can also extract values from Excel and some other third-party applications in which to optimize the designs and also drive the geometries. And then ProEngineer Mechanica also has a bidirectional integration with applications such as MathCAD and Excel to, again, import and export different parameters that are used in those types of calculations. So on the next slide, this just illustrates one example in particular. This is an airfoil flow design. And again, the mathematical functions were defined in MathCAD. There were some values and equations that we actually extracted from content in Novel to actually drive this particular design. And you can see that an array of points can be generated, and then these can actually drive curves and some complex surface geometries. And as the designer is doing what-if analyses and changes the input variables within MathCAD, the design and Pro Engineer and those geometries can automatically be updated because, again, there is that tight bidirectional integration.
Sandy, just one question about MathCAD here. I know that a lot of the people in the audience, of course, use computer-aided design package, Pro Engineer, and MathCAD in conjunction with each other, but MathCAD is an independent program, can also be used independently for calculations only, yeah?
Yes, that is correct. So MathCAD is a standalone application, and actually we have a very broad base of customers that exist outside of the mechanical design space, if you want to call it that. So I noticed on the call there are also some engineers from oil and gas. We have a very large number of electrical engineers as well. So again, a lot of these different types of engineers in different disciplines need to document their designs. They have some equations. The key benefit of MathCAD here is that they look like natural math equations, unlike other applications which might look more like a programming language. It's very hard to verify and validate those types of calculations, or even with Excel, when you have multiple cells that are referenced or linked to each other and the equations don't look like natural math, it can be very hard to read that. So this is an incredibly valuable tool to capture IP, share the IP, as well as improve verification and validation processes. And then MathCAD can also leverage a lot of the tables and the standards-based equations and constants that they need from various disciplines.
I've also heard you talk, Sandy, sometimes about, you sometimes refer to the CAD program as the what the design is, and the calculations and the equations as why design is the way it is. Want to explain that a little more?
Sure, that's correct. So a lot of what 3D CAD applications do is capture, again, the physical geometry of the product, what it looks like. Again, with some more of the advanced parametric modeling systems, they'll capture a little bit more of the design intent in what we call model-based design. But again, a lot of that information is hidden. So again, you'd have to kind of dig around through multiple layers of information to really figure out how something was designed. But again, the main purpose of that 3D CAD system is to really capture the 3D physical dimensions of the product. Whereas MathCAD is very complementary to that, and it, again, captures the thought processes behind how something was designed. So again, it captures text, the math, the graphics, various what-if scenarios, design of experiment analyses. It captures all of that intellectual property that, normally would just be written down, either in an engineer's notebook, actually a paper-based system, sometimes Word, sometimes in Excel, sometimes it's not really captured very well at all, and you just kind of see the end product at the end. But using MathCAD really captures, how something was actually developed, and can, again, help a company really retain a lot of that engineering knowledge and IP used throughout the process.
Okay, thanks, Sandy. All right, let's talk about sustainable design, because it is becoming something that a lot of the engineers are pursuing these days, or if they are not, they are interested in looking into it at the very least. There is a growing interest in sustainable design, so we now begin to see a lot more technical content related to the topic. Novel, for instance, recently added a new section on renewable energy and sustainability to its portal. So there's a whole bunch of titles, specific titles related to this topic that you can now, if you're a Novel subscriber, look into and export equations and tables from that kind of publications. So we can easily look up these, for instance, I don't know, maybe properties of biodegradable polymers and understand the rate at which they degrade or the wind speed at a certain area, and figure out how to take advantage of the potential energy that will come from that wind speed. So how should a designer incorporate that kind of information the kind of information specific to sustainability into their decision making. I want to start with Amy. Amy, share your thoughts on that, please.
Thanks, Kenneth. So we've just released a technology preview called Project Krypton, and it really focuses on helping our designers get a better idea of what their material choices have an impact on the environment. And this is particularly focused on plastics, and we're able to use some of our mold flow technology to allow a plastic part designer to make better choices up front and really evaluate alternatives when they have more flexibility to make changes. So at that early part of the design, when swapping out materials or trying to minimize material or make changes that impact manufacturing, can be done very effectively without incurring a lot of cost. So in this Krypton preview, you see 3 dials here that give upfront real-time feedback in 3 areas for our users. One is around manufacturability, so it helps you understand as you make different design modifications how that is affecting the manufacturing process for plastic injected molded parts. Also, we have one that looks at cost. So again, certain design changes are going to drive up your manufacturing costs, and it's great for customers to be able to both do things that are good for the planet and also good for their company's profitability. And then the most interesting one, I think, in many cases is the last one, and that's the environmental impact. Given the state of material models these days, we're able to understand how a material choice can really have an impact on the embodied carbon, embodied energy, and recyclability of the products that people are producing.
So, Amy, I understand that Krypton is a plugin for Autodesk Inventor, and it is at the moment, as the technology preview, available as a free download, is it?
Exactly. So we leverage a site called Autodesk Labs to kind of do things that are experimental and leverage technology in different ways, where we want to drive a lot of customer feedback and input to make them better.
Thanks. All right. Now, the next topic is actually my favorite topic. We'll talk about twisted metals and exploding assemblies. I'm talking about, of course, computer-aided engineering, simulation, analysis. Now, people who are familiar with computer-aided design programs would recognize that both Autodesk and PTC have simulations and analysis products. These are software that people can use to digitally put pressures and loads on models and then observe the effects. What I'm wondering now is, how can people take advantage of the specialized information they now have access to, like, thermal conductivity of recycled plastic, for instance? It's the same kind of thing that I could look up in maybe in a Google search, or maybe in technical content providers like Novel. When we have these kind of information, how do they incorporate these kind of information into simulation and analysis? Let's start with Sandy. What are your thoughts on that, Sandy?
Okay, Kenneth. So this type of information can be incorporated again in several different stages of the design process, and this workflow kind of illustrates that a little bit. So again, early and upfront in the design process, using some of this data about the materials from Novel and MathCAD, this information can be used to drive some of the geometries in ProEngineer, which hopefully gives you the performance results that would be validated in ProEngineer Mechanica, or even in the mechanisms application, which, again, these are applications where you would input the loads, as you mentioned earlier, boundary conditions, material properties used in your analyses, and again, simulate the performance of the part. But again, the key inputs here are based on what materials you're using. So if you flip to the next slide, ProEngineer actually has the capability to support some of these novel materials. Again, engineers are oftentimes pushing the boundaries of design both on the physical front as well as in the materials realm. Oftentimes companies have novel or proprietary materials whose input parameters or properties can't be found on their standardized chart. So they're actually characterizing the materials in real time and then putting in this test information into their simulation and analysis software to try to simulate them. If they don't have these parameters characterized about the material, they would then have to build an actual physical prototype and test the part, and then take the data from a longer, more costly process. So this slide here actually shows you how in ProEngineer today you can actually take your, again, the test input data from a material, we'll call it, a specialty polymer composite that's used here to bond these two metal sheets. We're looking at, the stress strain properties, and software is automatically calculating the Young's modulus, which would then be used in, some higher end CAE analyses within ProEngineer.
So I'm guessing, Sandy, that the material properties are very important because that is, after all, the one that can inform the digital model on how a shape, how a model will deform when you put it under extreme heat or extreme stress. Yeah?
Yes, that's correct. So again, oftentimes, based on the strength of material, you may have to actually thicken the part in order to meet your, the original product requirements for its performance. Oftentimes engineers are trying to make things lighter, smaller, faster, cheaper, but there's a limit in which they can do that, because it would violate other types of requirements that they've specified for strength. So again, it's very important to have very accurate materials characterization so that you can, design the right geometries of the part. And then also the software simulates this type of performance over time. So it's not a one-time testing. There are applications that do more fatigue analysis, and they test it over tens of thousands of cycles, especially with different materials that are biodegradable, whose performance degrades over time, and this happens with a lot of plastics as well. You want to know, if a product is out in the field for 3 to 5 to 10 years, is it still going to perform as if it were brand new? So again, the software is now very powerful and intelligent, and it can tell us these things through digital simulation as opposed to just real-time physical testing of a prototype.
Yeah, with the physical prototype testing, of course, you would have to break the physical prototype itself, which would cost money. But with the digital prototype, you can break it over and over again, and you're really breaking pixels in essence.
Right.
Amy, we'll turn to you now. What are your thoughts on that, using equations and tables and material properties and simulating and finding out results of your design?
Well, I couldn't agree more with what both of you are saying. The idea of having to wait and break a physical prototype over and over again through trial and error to perfect your design is not effective, and it's not the state of the art anymore. I think all our customers are using embedded CAE with the CAD model so that they can really do those explorations when they don't cost very much money at all. And so getting the material definition up front is important, and getting that specified in the system is really critical. But another area that we're looking at here at Autodesk is how do we get that simulation, how do we get that trial and error moved up front in the design process so that designers and engineers at the beginning of their designs can really explore different alternatives. So instead of waiting until the end and having an analyst or specialist do the simulation. So this is another technology preview we have up. It's actually a web-hosted optimization and analysis capability that runs embedded in Inventor. It's called Project Centaur, and it allows you to set up the stress analysis very quickly and to take a look at your parameters and then run a huge matrix of combinations so that you can optimize based on those parameters and quickly look at, because we're running this in the cloud, you can look at a huge number of different combinations and compare the results. And the cool thing here is once you've finished your exploration and you find the one that best meets your design needs, both in, could be things like weight as well as performance, you can now enter those parameters that you selected back into the design, and it will update automatically because you've built the design in a parametric equation-driven way.
So let's talk a little more about the fact that this is web-based. So a lot of the people are familiar with running simulations on a desktop application. The advantage of pushing the file onto a web server and running it in the cloud, could you get a little deeper into that? What are the advantages of that? Yeah,
so normally what would happen is, you'd set up a design, you'd run it on your computer, and you would be stuck waiting. It might take a couple of minutes, maybe not a long time, but because you're sitting there waiting and you can't really continue to work on your design, you're losing some time, and you might not explore as many options. But by setting it up and then pushing it up off into the cloud, you're able to run dozens and dozens, even hundreds of options, and still be able to continue working on your computer, working on your design or whatever other task you had to do, and then the results come down and you can pick and choose and sort through them. So it's a very effective way of harnessing that massive compute power in the cloud and then continuing to move on and work on your desktop.
I want to also go ahead and talk about the pros and cons of using equations and tables and computer-aided design modeling. We'll start with you again, Amy. What would you say are the pros and cons of using this method to design something? Are there any challenges? Are there any benefits? How do they outweigh against each other?
I think one of the biggest challenges probably people are witnessing in this presentation is that there's so many different options and ways to take advantage of equations and parameters and material models within a design workflow. So I think knowing where to start and getting some sense of where you're going to get the biggest impact can be the challenge. But on the bright side, I think there's lots of simple ways to get started with just the parametric-driven equations that help you build your model. And also, it's a great place to start by exploring a site like Novel to get that trusted information up front early and use that to help increase your productivity.
Yeah, and the trusted information source probably is an important point to talk about because we can look at, for instance, the biodegradability of or thermal properties of certain new materials that we may be experimenting with to make our design more environmentally sustainable or less impactful of the environment. But we really don't know if we look up something on Google, for instance, whether that information is vetted or whether that has been verified or whether that comes from scholastic sources or not. But if you find something on a Novel's portal, you can pretty much be certain that that's actually from a reputable publisher. And now with Autodesk products, Amy, I guess the material information, a lot of them, they come with a product like MoldFlow, which has an extensive material database.
Exactly, and with MoldFlow in particular, we're always testing latest and greatest state-of-the-art plastics to incorporate into that simulation. But I think no matter how extensive any vendor's library is, there's always new things coming into the market. So it's really important to have sites like Novel that you can go to, get the trusted information, and not have people spending lots of time searching when they really want to be doing their design work.
Thanks a lot. Sandy, same question to you. What are the pros and cons of using equations and tables? Are there reasons why people who normally use computer-aided design packages might be reluctant to experiment with equations?
Yes. So I think there are several benefits, and I agree with Amy. Again, it's a very powerful approach. It helps you predict the performance of the design up front and early in the process. If you look at the overall product development process, if you are doing variant design, product family tables, you can really leverage the power of equations once they are set up and linked into the design. There are also benefits in design verification and validation as they're streamlined by using, again, these standard-based equations, trusted constants, trusted information that can then easily be shared and reused. The one con to this method is that it does take a little bit longer to design products and really engineer them up front using these equations. So again, there's a lot of thought done behind it. There are a lot of calculations that are done much, much earlier than might be experienced in a typical process, just simple drafting process. So again, that may seem like it's taking longer up front, but it definitely saves you time in the back end if you're using equations to create these types of very intelligent models. So again, sometimes it's not the fastest method if all you're interested in is just creating 3D geometries, because you do have these equations. Sometimes you might have constraints. So if you're trying to modify some of these geometries and it's overly constrained, you might find that you actually can't make that modification. The CAD system won't let you do that if you're doing something that it thinks is wrong. So again, rapidly repurposing or making dramatic or radical changes to this type of design can be a challenge.
Let me see if I understand this correctly. I think I do, but you can tell me. So, for instance, if I specify that the wall thickness of my plastic pot is, say, 0.5 millimeter, and I can easily change that. If I change my mind, and if I find out something I want to do about that, I can just change it to 0.6 or 1 millimeter. Whereas if that dimension is driven by a mathematical expression, it is a little more complicated and it involves a little more work to make that sort of change. Is that what you're saying, Sandy? That's correct. It can be on a more complex part. So, and again, if you've added constraints, if you said, due to some design rule or company practice, this part should never be less than, half a millimeter in thickness or diameter, and if you actually if you put in that modeling constraint and if you tried to decrease your geometry beyond that constraint you added, the system would not let you do that. Versus, again, if that intelligence isn't built in, if you don't have those constraints, if you don't have equations, again, the modeling system would let you make any change to the geometry without giving you an error message or asking questions on, do you really want to make this change? It's violating something that you told me to do earlier. So, yes, you got that right. Again, so as you can see, there's somewhat of a learning curve, both from a personal and process perspective. In order to add the intelligence or in order to, again, integrate parameters from one application to another, there is somewhat of a learning curve to do that versus just simply opening up a CAD application and starting to sketch geometries right away. Thanks, Sandy.
So you do need to do that.
I just want to do one more live poll. Mike, if you can help me with that.
How would you use equations and tables to shape your design's geometry? And go ahead and choose all that apply. Would it be number 1, to build products that perform better under stress? Number 2, to reduce environmental impact? 3, to incorporate sustainable principles? 4, all of the above? Or 5, none? And let's share the results. Number 1, 51% said to build products that perform better under stress. And then 5% to reduce environmental impact, 14% to incorporate sustainable principles, 42% all of the above, 6% none. So, Kenneth, what's your thoughts on that? Any feedback?
Yeah, that's very interesting, Mike, because I wonder what will happen if we make the same poll, if we take the same poll, say, in about 2 years from now on, because I understand that using equations and tables to make sure that your parts perform better under stress or under extreme heat condition, that's a given. But there is also, I would say, an emerging interest in using the same kind of method for sustainable product designs, because at the moment, sustainable principles and product designs many of them are still in the experimental stage, so some people, rightly so, are skeptical about some of them. I also want to get the panelists' thoughts on that. Amy and Sandy, let's start with Amy. Amy, what do you think about the results that you're looking at right now?
Well, I'm really happy actually to see that 42% of people are looking at both product performance as well as environmental impact and sustainability. Because I think that the trick is 3 things altogether, right? For your designs to meet your cost goals, your schedule goals, your performance goals, but all the better if they can do that and have a better impact on the environment and maybe existing products. And that's the real challenge for a lot of our customers and the ones who are taking that first step into considering environmental impact and sustainable principles and other design requirements.
And Sandy, what are your thoughts on that, looking at these results?
Yes. So I guess I would say I'm surprised that that more people don't use equations to build products that perform better under stress. Again, sometimes it depends on the mix of the type of engineer, but I thought that number would have been a little bit higher. I'm very encouraged by the numbers that I see for people that want to reduce environmental impact as well as incorporate these sustainable principles. Oftentimes, there's a very heavy trade-off between cost versus using these types of materials or these practices. And sometimes, they're at at odds. And it's a very tough decision for companies, but people that believe in, again, incorporating some of these newer practices, that's very encouraging to see that.
Okay. Thank you, Sandy, Amy. Now, stay on the line with me. We will take questions, and we'll see which question should go to. Mike, I understand that there is also a representative from Novel who's present to help us address some questions.
Delighted to welcome Ross Graber, Director of Marketing from Novel. And Ross, how are you doing today?
I'm doing excellent. Thanks, Mike.
Good. Well, thanks for joining us. And Kenneth, there's a couple questions that I have here in the queue. Let me ask the first one the question is, what's the difference between looking up something on Google and looking up the same thing on Novel's portal? Maybe Ross wants to handle that.
Ross, so you should share your thoughts on that because I talked a little bit about that earlier.
All right. Well, actually, our users have found that the difference can be really big for them. And this is because of three things that we're seeing that make Novel different. The first thing that we're seeing is the content on Novel is vetted content. And what that means is the information's it's been taken from leading reference guides, and these are guides that have been published by over 70 of the world's leading engineering societies and publishers. So what this is telling us and what this means for our users is the content on Novel is content that can be trusted. And we know that for many of our users who use Google as well, they don't have that same level of trust with what they find on the web in general. Now, something else that we see and that we're hearing back consistently is that for engineering use, Novel search is a lot more precise. And the example I like to give is, well, try asking Google to help you find alloys that have a tensile yield strength greater than 50 KSI. It's really the sort of question that Google isn't going to do a great job helping you out with. And there's one final thing here. Novel is a system. It understands data that's buried in charts and graphs. It knows that these are objects which are made up of numeric values. And because Novel knows this, searches can return data values that are stored in charts and graphs and equations as well. Now, most web search engines, they generally look at objects like these as pictures. So it means they're not able to pull value from them and return them in their results in quite the same way. So as I started by saying, folks who've begun using Novel see a very big difference in terms of trust and ability to search and ability to find.
Thanks, Ross. What else? What other questions do we have, Mike?
Well, we have a question here that this is to both Sandy and Amy from Richard. It seems like our panel are advocating that digital testing is so good that actual physical prototyping is no longer needed. The question is that actually a good thing for now? So, Sandy, do you want to take that one?
Yeah, so as a blanket rule, eliminating all physical prototyping is not a good thing. I think, again, it really depends on the confidence in your design, if you've done it before, if you've used that before, and if you've at least done one physical prototype to validate a lot of the simulation that we're doing. It's not a complete digital simulation. Today isn't a complete replacement, but it does reduce a lot of the number of cycles that a company might have to go through. But it's always good to do one final gut check to kind of test that out.
Thank you.
Mm-hmm.
Amy?
So I agree completely. I think the goal is really to reduce the number of physical prototypes. There's always going to be certain times where you're going to want to have a physical prototype. Some of those cases are in perhaps consumer products design, where you want to be able to hold and feel and really understand something you're not going to get, no matter how great your simulation or how beautiful your visualization is on the computer. The other thing I'd want to mention is that rapid prototyping isn't something we really covered here, but the ability to print your design in a way that allows you to get that kind of tactile experience and be able to touch it and hold it and everything is another aspect of prototyping that's kind of in between the full-blown functional made with the actual material physical prototype and the digital prototype.
Great. Kenneth?
Yeah, you know what? I agree with both panelists here as well. I wouldn't recommend eliminating physical prototyping and physical testing altogether. But what it does make sense is in the cases of something like automotive industry, for instance, building if you're physical prototyping, say, a coffee mug or a coffee maker, that's a fairly easy expense to handle. But if you are an automotive maker, if you have to build a clay or a foam prototype, we're talking about 250,000 to $1 million in rough estimates about how much it will cost to make that prototype. So if you can replace using 3 or 4 prototypes to issue a new car model, instead you can reduce that to 1 or 2 prototypes. You're making a huge dent in your budget, in your project operating costs. So that's why I think digital prototyping has found a lot of, it's very appealing to many of the engineers these days. What other questions do we have, Mike?
Well, we have a couple, and again, this is going to be tossed back to Sandy and Amy. So this is from Dell. How far into the product manufacturing process can equations and tables and parametric CAD computer-aided engineering be used? And the second part is product customization by customers a possibility? And I guess Kenneth will let you chime in at the end. So Sandy, if you want to take this one.
Sure. Again, if you remember that little process flow chart that I showed earlier, you can start using these equations at the very beginning, even before you start modeling anything in CAD. So even in the product requirements phase, as you're trying to figure out how big, large, or what color, what material something should be made out of, you can start leveraging these equations right away. So again, the combination of novel math used there with MathCAD would be great right at the beginning. You can do a lot of functional design and predictive engineering and get a good sense, first-order approximation of what a design should look like before you start your CAD modeling. And then once you do start CAD modeling, again, there are products within ProEngineer, and I'm sure Inventor has some as well, where, again, you can use these tables, again, leverage them in some behavioral modeling simulations, and, again, do some more serious, larger-scale what-if analyses. And then, again, as you're moving down through that product development process, you can continue to input and leverage some other additional types of equations in your CAE processes as well as manufacturing.
Thank you.
I wanted to answer Amy as well, because there's another aspect of this that we found to be interesting is now that we've got our mold flow product hooked up to our stress analysis product, you're able to actually get the as manufactured material model out of the plastic injected molding simulation and use that to do your stress analysis. So rather than looking at like a uniform material, because a plastic will change as you melt it and mold it, you can actually understand the as manufactured simulation. So that gets you a little bit closer to not needing as many physical prototypes. The other thing that you can do is you can start to use some of the visualization technology with the simulation results. So if your simulation is showing you're going to have some divots or some imperfections in your plastic part design, it's one thing to look at the rainbow-colored simulation output, but another thing to be able to look at the different finishes you can put on that model photorealistically and see if you can hide the imperfection with a finish as opposed to having to modify your design.
Kenneth, would you like to have some closing comments? Because we're getting pretty close to wrapping up today's excellent webinar, and I have some final housekeeping bits to give out.
Okay, well, sounds good. I just wanted to thank, I want to convey my wholehearted thanks to both panelists, Sandy and Amy, because I could not have imagined a much more lively and much more informative discussion than the one that we've just had. So, and I also want to thank the audience for joining us, and we hope that we give you some food for thoughts and inspire you to incorporate mathematical expressions and interactive tables into your CAD modeling sessions. Now, if we can go to the final slide for me, Mike. Yeah, thank you. If you can think of a question after you hang up and you'd like to engage us more in a much more substantive discussion, we are open to it. We're open to keeping the dialogue continuing. So visit my blog, Desktop Engineering's virtual desktop blog, and find that post titled Incorporating Equations and Tables into CAD. We'll keep the dialogue going. We'll welcome your comments. Mike, back to you.
Kenneth, thank you, and thank everyone in the audience for your attention today. We really appreciate it. And again, special thanks to Sandy and Amy and Ross, and of course, you, Kenneth, for doing a phenomenal job of moderating this panel. And extra thanks to both Desktop Engineering for sponsoring today along with Novel. And we really are looking forward to getting the questions that unfortunately we couldn't answer on air back to some kind of response back to you. And as I mentioned, all of you will be receiving an email with a link in it on how to get a copy of this recording. One last request. Please take a moment to fill out the survey. It'll be in your browser window in just a moment. And again, this is Mike Agron as your moderator and Tamara Williams as your producer saying thank you so much for joining us. Have a great rest of the week, and bye for now.